So we're going to continue with the idea of vectors, and what we're going to talk about now is what's called the dot product. So the dot product is another operation that you can do with vectors, and you're actually going to operate a vector with another vector this time. But when we do this, this isn't going to result in a vector, it's going to result in a scalar. So that's an important thing to keep in mind. So the way we define the dot product is if we have a vector u and a vector v, basically what we're going to do is u dot v is going to be the product of the x components plus the product of the y components, and that's all there is to the dot product. Okay, so let's say we had a vector 3, 4. Let's say that that's u, and let's say that v was 5, 6. So u dot v would be 3 times 5 plus 4 times 6. So that would give us 15 plus 24, and that's 39. So u dot v would be 39, and that's all there is to the dot product. With the dot product, we get a few properties that we can use to simplify our work. So kind of like with numbers, if you have u dot v, you can do the dot product in any order. So u dot v is the same as v dot u. A is our scalar this time. I apologize about that. So u and v are vectors, as well as w, and a is a scalar. So u dot v is going to be the same as v dot u. If we multiply a scalar by the vector u and then dot product it with v, that's the same thing as if we multiplied the scalar by the dot product of u and v. Furthermore, if we have a sum of two vectors dotted with another vector, we can distribute that dotted vector into the sum, and so we get the dot product of u and w plus the dot product of v and w. And finally, if we have the magnitude of u and square it, that's just the same thing as if we were to dot u with itself. Okay, so those are our four main properties of the dot product. So I want to just go through and show you why some of these are true. So the first one we're going to show is that u dot v is the same as v dot u. So what I would do first is start with u dot v, and we're going to define this dot product. So let's say that u is the vector a1, b1, and v is the vector a2, b2. So let's define this dot product. So u dot v is going to be a1, a2 plus b1, b2. Now, we're working with numbers at this point. So we're past vectors, we're into numbers. And we know that numbers can be multiplied in any order. So we can flip-flop the order of a2 and a1 as well as the order of b2 and b1. So we get something that looks really similar, just in a different order. So now what we're looking at is actually the dot product of v and u, because we've switched the order of a and b. So this is v dot u. And because we've done equal signs all the way down, that shows us that these two statements are equal. Okay, so it's very similar to the identities that we proved earlier in the class. Now let's look at the magnitude of u squared. So the magnitude of u squared, let's think about what the magnitude of u is. So this time let's just say that u is ab. Okay, so the magnitude of u will be the square root of a squared plus b squared, and we're saying that that's squared. Alright, so that's the magnitude of u squared. Now, if we square a square root, that's going to give us what's underneath the square root. So we just end up with a squared plus b squared. Now, if we think about what those exponents mean, and we expand out those products, what we get is a times a plus b times b. Now, you might notice that that looks familiar. That is just u dot product with itself. Sorry, that's not a v. So that's just u dot product with u. and that is why that property holds true. Okay, so that's just a few little proofs for you to get you into that mindset. So now let's practice by calculating each of the following dot products. First, we have 4, 5 dotted with 2, 3. So this is just going to be 4 times 2 plus 5 times 3, which is 8, plus 15, which is 23. So the dot product of those two vectors is 23. All right, the next example, we have 2, negative 1 dotted with 1, 2. So this is going to be 2 times 1 plus negative 1 times 2. So what we get here is 2 minus 2, and that is 0. So just keep in mind that a dot product can be equal to 0. That is totally fine. Okay. The next example, we have 0, 3 dotted with 4, negative 2. So we'll do 0 times 4 plus 3 times negative 2. So we get 0 minus 6, and that is negative 6. All right? Okay, so now we're going to do a little bit more complicated examples. So these will require some order of operations, but again, order of operations with vectors is really similar to just regular numbers. Okay, so for the first example, we have u dot v multiplied by w. So since u dot v is in parentheses, that's the operation we're going to do first. So let's go ahead and sub in all of our vectors. So we have vector u, which is 1, negative 1, 3, dotted with v, which is 2, negative 4, and that's going to be multiplied by w, which is 1, negative 2. So let's do the dot product first. So we have negative 1 times 2 plus 3 times negative 4, and that is still multiplied by 1, negative 2. So continuing with simplifying this dot product, we have negative 2 minus 12 multiplied by 1, negative 2. So negative 2 minus 12 is negative 14. And again, that's still being multiplied by 1, negative 2. So now what we have is that instance of scalar multiplication that we talked about in the previous video. So to do this, we just need to multiply each component of the vector by negative 14. So we get the vector negative 14, comma, positive 28. So that is how you would simplify this more complex expression of vectors. Okay, now let's try one where we do a scalar multiplication first and then dot it with a vector u. So we have vector u dotted with 2 times vector v. So let's go ahead and sub in our vectors. So we have negative 1, 3, dotted with 2 times 2, negative 4. So just like with numbers, you want to do this multiplication first, okay? So let's do that. So if we multiply the vector 2, negative 4 by a positive 2, we get the vector 4, negative 8. Okay, and now if we want to dot that with negative 1, 3, we get negative 1 times 4 plus 3 times negative 8. Negative 1 times 4 is negative 4. 3 times negative 8 is negative 24. So this answer is just negative 28. Okay, so depending on the order in which you do your dot product and your scalar multiplication, notice that you could get an answer that is a vector, or you could get an answer that is a scalar. It totally depends on what is your big operation that you're doing in the expression. Okay, so now we come to what is called the dot product theorem. Okay, so now we're looking at the angle between two non-zero vectors u and v. So if theta is the angle between two vectors u and v, then we can say that the dot product of u and v is equal to their magnitudes multiplied together times the cosine of the angle between them. Okay, so that might seem a little strange, but let's try to show that this is true. Okay, so let's draw a picture of what this looks like. So let's say we have this is 0. Let's say we have some vector v and some vector u. Okay, so those are our vectors v and u, and note that these are arbitrary, so you could draw these anywhere you want in the plane, but just to keep it simpler, we're sticking to quadrant 1. Okay, so let's call this point here, let's call that, actually let me relabel this. Let's put our vector names here and here because we need to label our points. So we'll call this point B, this point A. Our angle between our two vectors, theta, is right there. And let's think about this side right here, which if you remember from our geometric addition of vectors is going to be u minus v. Okay, so now let's apply the law of cosines to the triangle defined by the vertices A, O, and B. Okay, so let's just write all of this stuff in the triangle together using the law of cosines formula. So what we get is, you can think of vertex O like angle C, if that helps you. So what we're going to get is the magnitude of u minus v squared is equal to the magnitude of u squared plus the magnitude of v squared minus 2 times the magnitude of u times the magnitude of v times the cosine of theta. Okay, so all we've done again is just plugged in all of this information from our picture into the law of cosines formula. So just as a refresher, that would be c squared is equal to a squared plus b squared minus 2ab cosine c. Okay, so you can see how that matches up. So now let's do some simplifying. So if you think about squaring the magnitude of u minus v, what we would get is the magnitude of u squared minus 2 times the magnitude of u times the magnitude of v plus the magnitude of v squared. Okay, and this is still equal to the magnitude of u squared plus the magnitude of v squared minus 2 magnitude of u magnitude of v cosine of theta. All right, so let's see what we can cancel here. So the magnitude of u squared is going to cancel on both sides, as will the magnitude of v squared. So what we're left with is negative 2. I apologize, this isn't the magnitude of u times the magnitude of v. This is u dot v. Okay, so what we have is negative 2 times u dot v equals negative 2 times the magnitude of u times the magnitude of v times cosine of theta. All right, and so if we divide both sides by negative 2, we're just left with u dot v is equal to the magnitude of u times the magnitude of v times the cosine of the angle between them. Okay, so that is why this formula works. All right, it's all based on law of cosines and geometry. Okay, so now let's rearrange this formula to actually find the angle between two vectors. So remember, our original formula was u dot v is equal to magnitude of u magnitude of v cosine theta. So notice, if we were to just divide those magnitudes to the other side, we would end up with this angle between two vectors formula. Okay, so that would cancel out here, and we're just left with cosine theta is equal to u dot v over magnitude of u times magnitude of v. So while the first formula wasn't particularly useful, this one is, okay? And it's the same formula, again, it's just rearranged. So let's practice by finding the angle between u equal to 4, 3 and v equal to 3, 5, okay? So let's start with our formula. So we have the cosine of theta is equal to u dot v over the magnitude of u times the magnitude of v. Okay, so what I like to do is just go ahead and find the magnitudes off to the side so it leaves your formula a little cleaner. So the magnitude of u will be the square root of 4 squared plus 3 squared, which is the square root of 16 plus 9, which is the square root of 25, which is 5. All right. The magnitude of v, on the other hand, is going to be the square root of 3 squared plus 5 squared. So that'll be the square root of 9 plus 25, which is the square root of 34. And I don't think we can simplify the square root of 34, so we're just going to leave it like that. All right. And finally, we could go ahead and find the dot product of u and v and just sub everything into our formula. So the dot product of u and v is going to be 4, 3 dotted with 3, 5. So that will be 4 times 3 plus 3 times 5. So that is 12 plus 15, which is 27. Okay? So what we end up with is subbing in our dot product. We have 27 over 5 times the square root of 34. Okay, so that's everything subbed into our formula. So now if you notice, we have cosine of theta is equal to this fraction. So to solve for theta, what we can do is take the cosine inverse of both sides. So we get that theta is the cosine inverse of 27 over 5 times the square root of 34. And if we were to plug this into a calculator, and keep in mind, calculator should be in degree mode, okay? So if your calculator is in degree mode and you plug this in, you should get approximately 22.166 degrees, okay? So all this is telling you is if you graphed the vector 4, 3 and graphed the vector 3, 5, and you measured the angle between those two vectors with a protractor, you should get roughly 22 degrees. All right, so that is the angle between your two vectors. Okay. The last thing that I want to talk about with vectors is orthogonal and perpendicular vectors. So we say orthogonal instead of perpendicular when we're talking about vectors because you could have a vector in more than 2 dimensions, in which case perpendicular doesn't really make sense, okay? So we call them orthogonal, but in 2 dimensions you can think about it as perpendicular. Okay, so 2 non-zero vectors are orthogonal or perpendicular if their dot product is equal to 0. Okay, so as an example, we're asked, are the vectors u equal to 2, -3 and v equal to 6, 4 orthogonal? So to test for orthogonality, what we do is find their dot product. So u dot v is equal to 2, -3 dot 6, 4, and taking their dot product, this is 2 times 6 minus 3 times 4, which is 12 minus 12, which is 0. So because our answer is 0, we would say vector u and vector v are orthogonal. So when you're doing a problem like this, it's very important to state this conclusion that u and v are orthogonal because that was the question. It wasn't just find the dot product, it was find the dot product and tell me your conclusion based on that dot product. So that is a little important there. Okay, So if we're talking about perpendicular vectors, your next question might be, well, can vectors be parallel? And the question, or the answer is yes. So two vectors u and v are parallel if there is a non-zero scalar alpha, so that some vector v is equal to alpha times, this should be a u, I apologize. Okay, so vector v is basically some multiple of vector u. Okay, so now for this example, we want to show whether the vectors u equal to 3, 5 and v equal to 2, -8 are orthogonal, parallel, or neither. Okay, so first let's test for orthogonality. So for orthogonality, we would do u dot v. So that is 3, 5 dot 2, -8, which is 3 times 2 plus 5 times -8. So that is 6 minus 40, and that is -34. So obviously here, -34 is not 0, so these two vectors are not orthogonal. Okay, so now let's test for parallel. So for parallel, we can check slopes. Okay, so remember that a vector is just a line, so we need to find the slopes of these two vectors. So the slope of vector u is going to be y over x, which is 5 over 3, and the slope of vector v is going to be, again, y over x, which is -8 over 2, which is -4. Okay, now I think it's pretty obvious here that there is no way that 5/3 is equal to -4, and so we know that these two vectors are not parallel. Okay, now just to give you an example of two vectors that would be parallel, let's say as an extra example that you had the vector u equal to 2, 4, and you had the vector v equal to 1, 2. Now I think this example is kind of obvious, but it's a good, easy example to start with. So to show that these are parallel, all you have to do is either check their slopes or show that one is a multiple of the other. So in the case of the vector 2, 4, what we could do is factor out a 2, and we would end up with the vector 1, 2. So what this shows us is that vector u is 2 times vector v, which shows that these two vectors are indeed parallel. Okay, so that's just an example of two vectors that would be parallel. All right, so I know this was a short lesson. Hopefully that made a little bit of sense. And just make sure that you're working on a few of these exercises. It's not too many. Main thing is focus on those exercises from the previous part of this lesson.